Alright, so in chapter 1, what we're saying is memory is one of the key aspects that an OS uses to protect itself. Because if processes are running and the processes are allowed to cross boundaries, then that means that all security is lost. Anybody can write anything to anywhere. So the hardware is involved again. So last time, remember we said that even for protection, the first thing the hardware was doing was, it was making sure that it had dual mode, kernel mode and user mode. Meaning that when a code is being executed, any instruction was being executed, it actually knew that somebody was what? Either an admin or a normal user. Right? So code by itself, when it's running, the hardware has to help. Without hardware support, it was impossible. So today we are seeing a few more. So I pulled them, I listed out the extra registers. So we always say, in earlier chapters, we say, the OS, when it's switching between processes, has to switch the registers. Right? And today we are going to see why some of those registers are important. Right? And it's saying that for addresses, normally there's the physical address and the logical address. Right? So a physical address is a fixed address. For example, I can say room number 1. Everyone will know where room number 1 is. Right? Or room number 2. Or room number 3. So some of the things, we know exactly where it is. But then we can have something where it can be logical. Which means that by a label, I can tell you where it is. So if I say, where OS is being held, that one is more logical. That means that you have to do some mapping, some translation before you find the address. So if today OS is being held in this class, then anytime you ask, so where OS is being held, that is where they are having the party. Right? So if you come and the OS class has been moved, then I say, where OS is being held, that means that either I remap where OS was to another room, maybe room 2 or room 3, or I give you the actual physical address of where the party is. Right? So human beings do this as well. We do have logical addresses in our own minds and physical addresses. Right? So logical would be, if you're trying to register, I'll say, go to the nearest branch. It's a logical, it's not necessarily fixed. You have an idea that wherever you are, your nearest branch, you compute it in some way, and you get to the branch of the bank or wherever the organization is. Right? So for addresses, there's physical address and logical address. Logical meaning that there has to be some calculation or some modification before you find the actual address. So if you come to campus, maybe next semester or next 2 semesters, you'll say, OS class. If you want to find, you go to the OS class. But in that semester, OS might not be in this room. Meaning that the description of go to the OS class is a logical one. It's not physical. If I say go to room 216, that's physical. It's fixed. There's no movement about room 216. Room 216 will always be here. Right? Room 217 will always be there. But logical means that what? There's now a label to it. Someone will say, go to the discrete math class or go to the database class. And those will all be moving amongst the physical addresses. So physically things, the physical rooms will stay for a while. But the labels of how they are used will vary. So that's the concept of logical versus virtual. At the end, we'll go through with numbers so you can see the difference. Right? Now, caching we also mentioned in chapter 1. Right. So caching, remember for storage. The storage, we had the hard disk, if you remember, there was also memory. But between memory and the hard disk, right, is the cache. And the cache is usually, right. So on the chip itself, there will be some data. So the other one that people will mention is, some people also say registers. Registers are like small numbers. Usually the registers, there could be maybe 16 registers, 32 registers. It's not a large number. Don't be like 1,000 registers. The registers are just like small variables that the program will use to do some calculation. The virtual address. So let me use Excel as an example. Okay, so I was going to do this as an exercise at the end, but maybe I should start now. Oh, sorry, it should be this plus 1. Oh, come on. Nine up to 10. And this would be this. This is nice. All right. So there are. So let's say this is a hotel with 40 rooms. Right. Come on, stop. Okay, so I have on the left, so people are asking about physical versus virtual addresses. So on the left, I have some hotel rooms. So let's say I have, let me make it even smaller. Let's say I have 40 hotel rooms that people can book into. Let's make it, right. And on the right, I have some reservations. So people are going to be coming to make reservations. Right. So the physical one, just like the rooms we have here, they don't move around. So if you take memory, so the hotel rooms in this case is representing your memory. Right. You can apply the same concept also to hard disk networks and so on. So physical just means that something has a fixed location. It's not going anywhere. But the problem is that the other things in the system are moving in and out. They are going up and down. Right. So let's say that a company, for example, DHL, not advertising for DHL, just an example, right, books and says that they want to have a certain number of rooms, right. As far as this is concerned, what usually, the colors are not coming out, sorry. Let me use a deeper color. Okay. So for every physical room, so let me just put it set. Let me do logical, physical. So whenever DHL, if DHL says that they want 5 rooms, right, what will happen is I can give them reservation numbers. But for each reservation, I point it to what? A physical address. So if you come and say you are ticket number 1, I could say, okay, maybe for you, since you people said that you wanted to be on the corner, I'll start it out, okay. I'll give you 1, 11, 10, 20, maybe 19. Right. So in other words, there's a physical address, which is the actual hotel room, and then there's the logical, which is when you bring your number, I map you to what? An actual hotel room. So if you come to me today, and today I've given you these numbers, next time you come, it might not be these numbers exactly. So the physical means, just like in the physical world, physical means that it's the physical location, like room 216. And the logical are usually addresses that we give, but we'll remap them for you. Right. And when this happens, that means that over time, so another company comes, maybe, okay, I don't know if EMS is still around. 2, 3, 4, 5, 6. So that means that for them as well, anytime they give me an address, I will translate it to a physical location. Right. The benefits of doing this is that you can you can pretend you have a lot of memory. Right. All I'll tell you is, oh, okay, you are coming. Okay, you wait. I'll go and prepare. And that means that there will be some shifting of processes up and down. But for the people who are in there, it will seem to them that, oh, he says that I have 5 rooms. And whenever you come, we give you a 5 allocation. So as processes go in and out of memory, it will seem to the processes that, like someone can even be told, oh, okay, you are reservation number 40. The memory doesn't even go up that high. But, let's see, 12, 13, 14, 15, 16, right? So even though the memory doesn't go that high, because I am doing this remapping strategy, anytime I give you a logical address, I'll map it to what? A physical one. And I can play this game of, oh, I seem to have so many addresses, and I'll keep booking people. Just like booking flights, I'll book as many as I want. But in reality, when it actually gets there, then I'll assign or I'll have planned for you that this specific ticket will go to this physical location. So the logical addresses are like tickets or reservation addresses. So they are not real ones. But in the computer, it has a plan. Oh, when you come, this is where they'll plan to put you. Right? So I hope you understand the difference between the physical and the address. The physical and the logical address. Oh, the virtual is the same as, okay, when you hear virtual, it's the same as logical. Right. So when they say physical, that's usually the one that's stuck. But when we say logical, it's the same as the virtual. So it's the same concept. It's the same thing. Virtual, it's used interchangeably in the book. It's the same thing. Right. So virtual means that it's not actually there. That's the idea. Virtual, like if I say, oh, room number 50, it's not really there. Maybe the day when you are coming. So it's like, if you look at, I think when we are doing exams, room by room, they may attach certain numbers to it. So that this chair will be chair number 1, number 2, number 3. It's just a virtual number. It's not really there. We haven't really decided that it's always. So next class, they could rearrange, and the numbers will be different. So if you come and say, database, I was in seat number 1. It's not the same as OS, I was in seat number 1. The physical location of the seats will vary. So it's the concept of virtual. It's not really there. But the virtual has to be mapped to a real location when the process or when you're actually using it. The virtual has to be put into a real location. Right. Your question? Okay. All right. So back to the excitement. All right. So you have the hard disk, memory, and then register. So hard disk is where we usually say it's permanent storage. But between the hard disk and memory, there's the cache, which is some amount of memory right in the CPU very fast. And sometimes there are even levels of cache, level 1 cache, level 2 cache, level 3 cache. So if you are buying a computer and you look at the specs, often if one computer is more expensive than another, if you look at it and they say, oh, someone has a better cache or faster cache, even though the CPUs are the same, they know that the cache is what's sitting between memory and hard disk. And that is what will prevent you from having to go all the way. Sorry. It's not here. It's supposed to be. Please do note, there's another type of cache here, but it's not. I'll describe it too. Right. Some of these are SSD based. Right. Sorry, so many things. All right. So there is a cache that is on the CPU next to the processor. Right. So if you can have some memory that is very close to the processor, then you don't even have to keep going all the way to the memory that you have slotted into your machine. So even if you just take the memory out for a short second, your processor might be able to run. Right? But eventually he's going to ask for data from memory and he will stop. Right? Because if there's no memory there, then there's nothing to get data from. So anytime you ask for information from hard disk, it comes into memory, which is very close, so it doesn't have to go to hard disk. But there's also the cache. So it's like the same idea of hard disk to memory. There's also something in the middle called cache, where the processes that are running, as they are getting memory addresses, he's keeping a short list close by of the most recently used. There are many strategies for that. But some of those, so that he doesn't have to keep going all the way to memory. Now, these days, there are some hard disks that also have cache on them, meaning that they don't always have to spin. Your hard disk, when you turn it on your computer, it has this spinning. For those with physical, the hard disks which are not solid state, they have these spinning behaviors. Like it's a disk in there that is spinning to get the data out. What some people have been doing is some of the hard drives also have some cache in there, meaning that he doesn't always have to spin. Sometimes if you ask him something and it's already in the cache, that means the hard disk also has some memory can keep things in. If it's there, he doesn't have to turn on the hard disk to spin. And if he does that, he can also save on performance. The registers are the fastest, but they are also very few. Right? It's just used for normal computation. Right? So cache is the other concept that you must start to think of. You can apply this in many sense. You can even web applications. That means something is always going to the hard disk. If there's a lot of caching, a lot of memory, he can store some things in memory or in cache, and he doesn't have to keep spending a lot of time waiting for data to come back. Right? Now, if you ask for memory, there's this concept of hit, miss, and store. If you ask for something, right? So, for example, if you are a CPU and you ask for something and it's in your cache, you can say, oh, I've got a hit. I've got a hit means that you don't have to go all the way back. It is currently there, right? If you say you've got a miss means that you ask for something and it is not in your cache. So now you have to you go and get it from memory, right? And if you go to memory, to the same concept to apply. Is it a hit or a miss? Hit meaning that it's there. Miss meaning what? You have to go even further. And even if you get to the hard drive, there are some software now where even when you are trying to run a program, it will tell you, I have to now download from the internet. It's the same concept. If it's a hit, it means it's on the machine. If it's a miss, it means that he has to go and download it and bring it down. So there's the concept of hit and a miss. The idea of stall means that if it is a miss, that means if you want some information and you don't get it, then you have to wait whilst the information is being brought to you. So if you are installing software and it says, I have to go and download, that means what? It's a miss, you have to stall until the data comes back. If it is running some sorting program and it realizes that the data is not in memory, it has to what? It has to store. That means you will be IO blocked while what? It's pulling from memory. So a lot of times, the algorithms that are concerned with memory management have to keep track of this idea of hit, miss, and a store. Right? So let's use our hotel analogy. Right? So for example, if room number 5, something happened, maybe I'm cleaning it up, and you come and say, oh, I want to go to room number 5. That means that whatever content you had in there, if it's a hit, it means that what? I have prepared the room for you, everything is fine. But if it is a miss, then that means that you have to wait, probably at the front desk, until the room is prepared, maybe your things are put back. Currently, I don't see hotel rooms where they are moving things around. But I think in future, it may be possible to have these, that's crazy ideas I have in the future, where you can have a portable, like, living area, which can maybe be moving around. So imagine you come to wake up Rekusu, and then you want to sleep. Some bed and some things will be shifted on a train somewhere, come and it will unlock in a room here. I mean, that's crazy, but that's what I'm thinking. Right. So those are the sort of things I think can happen. If we try to apply the things we see in software to real life, that means that people can move around very easily. You can just get to a place, you want to brush your teeth, do your studio, I mean, crazy stuff, but that's the concept. Right now, it seems we are not there yet, but I think one day we'll get there. Okay, so there are 2 addresses. There's the logical one. The logical is like your ticket. And then that one is mapped to a physical. So if you come and the room that we planned for you is not available, then that means that there is now a miss. You have to wait while we actually find for you. So that means we'll go through the list of rooms that are there and say, okay, oh, you know what? We'll give you, okay, room number 2 is gone. You like corner, room number 9. Okay, I'll give you room number 9. Right. So with the logical, that means you have an address, but it's not yet tied to what? A location. It's just like getting lunch. You get these chips or these sheets of paper, and they tell you, okay, it's going to be rice, but you don't know the actual place of rice that's involving you. So you have to wait until what? Finally, when you get there, then they assign your chit to a specific tray, and they put the food in there so that you are now ready. Right? But until then, the sheet you are holding is virtual. It's virtual lunch. You haven't eaten lunch yet. So that's what the concept means. So there are logical addresses and physical. Logical meaning it's not real. You're just giving a number. But anytime you are performing the action, we'll try and map the virtual or the logical to a physical one. Right? So human beings, we have been doing this. We just don't seem to call it that way. Or even an airline reservation too is like this, where sometimes you book a ticket, they can say, oh, pick a seat. And then you may be able to pick a seat. Sometimes they will say, oh, this, you don't know yet what the seat is. But when you get there, they will try, and once you book the ticket, they'll give you a seat. Meaning that you have a ticket. Meaning, oh, I know I have a seat on the plane, but I don't even know. Sometimes you don't know exactly where you are. The only person who knows where he's sitting is the pilot. That means in the operating system, the OS knows where he's sitting. The OS has a designated location. He's sitting here. Nobody is going to take him from there. But the passengers, who are the users? When you get there, they may tell you seat number 1, seat number 2, seat number 3, seat number 4. They will move you around. Right? So how people understand the concept? Right? Or bus, those people who use public transport or not, VIP, you go and get your ticket. When you get there, then they give you a seat. The same idea. There's the what? Logical or virtual. And then you are given a real seat when it comes to traveling. Alright, so back to action. Right. So we have this idea of hit, miss, and store. And that concept is applied to memory and all the caches. So anytime if we say memory and someone says, oh, I have a hit, that means that the data was there. It's cool. If it's a miss, he has to what? Go one level up more in memory. That means maybe go to hard disk to find it. If not on disk, then someone may say, right now I see that most people are just used to computers which live in one place. Right? But on server farms and so on, if let's say a client wants to run some software and you don't have a hard disk that is on, there could be some place where you have archived all your older disks. And so then you can go and unplug. If you ever have the opportunity to visit like the IT office, you see that the laptops, sorry, not their laptops, their servers, taking out the hard drive is very easy. It's just like, it's like you can pull them out. You don't have to use any screws or anything. The hard disk, so don't go and steal any hard disks. Right? When I was in school, someone stole the hard disk for the OS class. Right? I think he was being late and he just wanted to make sure that nobody could submit. So he went and then he pulled out the hard drive. So the hard drives of the servers, usually they are very easy to remove. Right? And so the idea was, if anytime you're an administrator, there can be many, many hard drives. The main one, so if you take like SIS or something, I will have a hard drive that has the operating system. I have a hard drive that has usually the data we are working with. And I have a hard drive for archiving, which is the backups and things like that. So if ever I need to do anything, often you may have to take our hard drive and put in a backup disk. Right? And sometimes the things are mirrored. It means that the OS disk, there could be two versions. The data disk, there could be two versions. So even if you unplug one, it can still be working while you swap things out. Right? So that's the concept. Right? Now, the registers that are used to accomplish this protection, there are 3 of them that I've mapped out for you. Right. So I'll just show you this diagram before we move. So if you look at any process has a boundary of addresses, a lower and an upper. Right. But between the lower and the upper, there's the first address, so let's say 3000, and there's a limit to how much extra I can add onto that address for you to stay in your space. And for the addresses, for the registers, what they do is, whenever we are switching out, a process, we keep track of the base, that is the lower address, the limit. The limit is like how many addresses you can have. So if I say, oh, this first row is for maybe, okay, since we're only boys, 3 chairs. So I say, base is 0, 1, 2. And the limit is what? 3. Limit is like how many of those addresses I'm giving you. Right? So usually there's a lower limit and something that you can add to it to determine what is the upper bound. Right? So whenever you are trying to do any memory access, what they'll do is they'll try and compare to see if the address that you're asking for is between the base and the limit. If it is within that range, so we'll first ask you, oh, is your address greater than or equal to base? If it's greater than, it means that what? This may be good going on. And we'll check, okay, is it something that if we add the limits, you don't go over? If you go over, that means that usually you get an error. So in Windows, sometimes you see an error that says a process tried to access memory, or someone tried to access a location that was not for them. And they'll get like a blue screen. Or sometimes there'll be like a prompt on the screen with an exciting sound, bam, bam, and then it has to stop. Right? So in that case, if the 2 checks are done, so this is only for when you're dealing with purely physical address. Right? You check the lower, make sure you don't go above the upper before you allow the person to access. And all this is done in hardware. And hardware can do things very quickly. So if you think of the fact that computers now are saying, okay, some are running at 2.6 gigahertz and so on, that means that it's just a matter of what? An addition, some comparisons, a few cycles, maybe less than 10, you should be able to quickly do this. So the moment it loads any address, it can quickly, within a cycle or 2, tell if what? You are actually within your range. But that means that any process that is coming, if it's Microsoft Word, when he's coming, he'll come along with this what? This is my base, this is my limit. If Notepad is coming, Notepad knows that what? This is my base, this is my limit. So if Notepad tries to access any address beyond his limit, he will be killed. That is, trapped to OS monitor, address error. And the OS usually will kill you. Right? If you are trying to go beyond bounds. Right? Now, in this, there's this, what's this called? There's this, it's often used in security. It's a term you hear, like buffer overrun. I don't know if you have heard about those. Like buffer overflow, Buffer overflow, right? Meaning that if we are all assigned certain spaces, somebody may what? Overstep his bounds. Often, if those people are not killed, then they can steal data or cause some damage. Right? For systems where many things are sharing the same space, like a web browser, so there are many plugins, if they all live in the same space, then there's the danger of that issue. Because then, the OS will assume that all of you belong to the same space. He'll assume, okay, maybe Flash is running, he's still in your space, that is good. But then maybe one website wants to steal your data, and one is a legitimate site. So if you are not careful, so that's why a lot of the attacks on computers, a lot of them tend to happen through browsers or through plugins. And that's because often those plugins, when they are in a process, would all be what? Sharing the space. So if somebody is misbehaving, That's why often Adobe, Flash, and so on. Whenever I've seen these days, if your Adobe or Flash is not up to date, sometimes they'll just show an icon saying you have to update before they even load. Because they know that people have been using some of their plugins to misbehave. Because once the plugin is loaded, that means that he's within the space. If it's Flash, he's within the Flash space. He can do anything. Right? And the difficult thing is, software is harder to trick. Right? If it's hardware is like there's a button you have to press. There's no way that software can press the button. So that means that this logic is done within what? Hardware. The same way that the other one with the two modes, kernel mode, user mode, that was also done in hardware. So that software, once the OS gives you, then you can do it. But if the OS doesn't give it to you, software can't by itself go and change something in the hardware. So there has to be some protocol. So what they usually do is, base and limit. Now we are going to extend this idea by adding the logical address. Right? So anytime you are asked to access something, what they'll do is, if it is a logical address, I first of all have to add, so if it's logical, so let's take, where's my Excel? It's here. For each of these, there is some number, right, that I can add to your logical address to shift you to your room, right? So even though you come in logical 1, that means somebody, his relocation is 0. He's staying in the same place, right? That means that there is some number that I'll add for anybody who is renting. So I know you are number 1. But number 1, for me to map you, I can have another number that I add or subtract from your ticket number to get your actual room. And anytime you come, I guess what? I add or subtract that number. So for example, this is 0. I have to add 9 here. I have to add 7 here. Here it's 16. Here it's 4. Right. Now, if one process, now obviously it's easier if it is a block, so that you treat the whole process as one. So for example, if Dell is operating on all of these, I think these are in sequence. Let's use green. Right. For these guys, it seems that it's -4, right? That means that for the entirety of the Dell space, they are using what? A relocation of -4. Right. So the simplest one, so in terms of complexity, the first, which is very easy to do, is to say for any process, what? Every process just gets what? A continuous set of rooms. Just like booking for a conference or booking for a trip. It's nice if you get what? A continuous set of rooms. And also the first person stays in this case, room number 2, second person, room number 3, third person. It's nice if it's all together, right? But the problem with this is it doesn't always work out, right? Because in memory, things come in and things go out. So what if one day you come and then what? You can't get a continuous set of rooms. That means I will have to break the rooms into pieces, like in the Dell case, where different rooms are mapped differently. Not all of the rooms they get will be together. So that means that there are different mappings, different relocations involved. So people are understanding the concept. It's just like hotel room management or resource management. The first level, it's very easy. If you always get a continuous set of blocks, then you can just have one number and say, okay, for the EMS, whenever they come, subtract 4. But sometimes, over time, so I think people have heard of the term fragmentation, maybe, in hard disk. So as you copy, move your files on, off, you download a movie, delete a movie, download music, delete a music. Over time, some places are used and some places are not used. So for example, in this case, let me see the ones that are used. 1 is used, 11 and 10 are used. 2, 3, 6 is used. 12, 13, 14, 15, 16. Right. For the rooms that are left, if someone tries to get 5 rooms, it's unlikely they'll get them in order. Right. That means that for the hard disk, that's what management is going on, where files are going to be split into different locations. The same way for memory. When a program is running, if it will not all fit, then there has to be also a strategy to what? To break it into rooms or pages or blocks, and then keep a list of those things, not just to say there's one limit and one end. I could give you an array of limits and ends, so that if I know that you didn't get one continuous space, now when I'm asked to go and check, I don't just check one base and limit. I go and check the list that I've given you, your first base. So if, let's say, Ashesi came to book, let's give Ashesi a new block. Right. And they wanted, the remaining rooms. So they want, so there are 7 more rooms. That means that there will be 7, 8, 9. This is the virtual. This is the physical. Relocation. In this case, relocation is -4. And the others, 17, 18, 19, and 20 was already in use, wasn't it? Yeah. 20 and 9 are in use. So sorry, they can't even get all the rooms. Okay, so I won't even get up to 9. Then I have to go to 17, 18, 19. Right. And the relocation is now different. So one is 4, 4. This one is +4, +4, +4. Right. So that the first strategy of, let me give you a block, that is for maybe a computer that is very old. The algorithms are not well done. Right? Because if the computer strategies, I always want to give you consecutive memory. What is it going to do if it doesn't get consecutive block? Does it mean that you shouldn't run? If the first algorithm of how consecutive is what you are using, then maybe when someone asks for memory, you tell the person, I'm out of memory. Right? But a smarter approach would be, maybe you should keep a list of what? Base limits addresses for each process, so that you can have for one process many places where he's running from. So as far as Ashesi is concerned, they have a consecutive block. They'll say, 11, 12, 13, 14. Right? You can even trick them even further. Right? So what some OSs will do is, for every program, as far as the program is concerned, his rule number 1 is 1. Question?
Sorry, so in data structures, we learn about hash tables. Isn't that,
this is almost like a hash. So this is more like a lookup. A hash is usually computed. You can use hashing techniques for this one, but just make sure that for anything you pick, you can get the same address. But the problem with a hash is, usually for a hash, for a given input, you get a specific output. For the OS, he will need to move that thing around. So rather than just a hash computation, it's a lookup. That means that it's an array where it contains, for every address, where am I sending? For every address. I hope you see the difference. Hash, usually, if you put in a number, you always get the same result. But that's not going to work here. Because sometimes, what if you have put someone there already? You need to put this person in a different location. I hope you're understanding the point. Hash versus this. So this is not really a hash. This is more a lookup. Question?
So you were talking about fragmentation.
Mm-hmm.
Are you saying that the OS, after running the program over some time, is smart enough to say, let me give this space?
So even though to us, so the last thing I was pointing out here is, for example, Ashesi here has been told that they have Ashesi number 1, Ashesi number 2, number 3, number 4, within the Ashesi context. But then in virtual memory, there's some addresses they have been allotted. And then in the physical, there's a different set. So even for specific programs, they can be sort of not tricked, but made to believe that they have free reign. Right? Because if I say, I want room number 100, if you have not used up memory, then so now, if you are using memory, that's beyond what I have. If nobody else, let's say the DHL people, they are currently not on the campus, they are not currently using it. What I'll do, if you ask me room number 100, I'll go and take someone, move him out of what? Memory, put him to disk, and then give you that space. But then you will think what? You have more and more memory to use. So that's what the OS does to processes. They will slow down. That's why they will slow down. I mean, when you are running out of memory, it's not like your program will just crash. What will happen is it will just keep becoming slower, because now what? It's playing this trick. Like if I tell Ashasi people that, okay, you know what? I can get you these 6, 7, all for Ashasi, all for you, right? All for you. I'll get you all these spaces. You are booking, and I'll tell, okay, don't worry, I'll get you room number 5, 6. Oh, don't worry, I'll do it all for you. 6, 7, 8, 9, 10. So in Ashesi space, they are told they have 10. But the trick is, anytime you ask for something, if you are the guy who's currently running, then I'll say, okay, you want one more room, number 6, eh? Okay, now I'm going to take somebody, move that person off to the hard disk. That means 9 is now no more in use in the list I have, and then come and give you 9. And I have a new offset for you. Right. So this is the game that the OS is playing. So one program can think, oh, I even have 10 gig. Maybe you don't even have 2 gig. But you can say, well, you want to run 10 gig, that's fine. You can see your virtual box has that behavior. I think sometimes, I don't know if they kindly force you to not go over. But you can go over the limit of how much memory you have. But all it means is that when you are asking for memory outside of bounds, they'll be switching, copying data from memory, taking to hard disk, and bringing it back, and renumbering it. Right. Means that if I share see, then say, okay, I want room number, more rooms. Since DHL people are not here, not currently running, I can move all these people off. Right. That means take them out, and the ones I took out were, 1, 11, 10, and 20. And I'll say that currently 1, 11, 10, 20, right, are in. So this is a game that the OS plays. If you ask for memory, that's not there. What? But you know that he has to keep track of which process actually has the physical memory. Because then if DHL comes back to ask, right, you don't want it to be having clashes. So you have to keep track of those ones that you have assigned, those processes, what you're giving to them in memory, and then the ones that you have shipped off to hard disk. So that if someone asks for something and it's not in memory, you have to what? Swap out. Now, it's possible that if DHL comes, he may not get the same location. Let's say DHL number 5 is coming back, but he was previously in 9. 9 is no more available. So I'll come back and say, okay, there's 5. Then I'll go and search, is there some process who is currently not using his memory space? Then I can take a piece of it, maybe the EMS guys, they take a piece of somebody, and say, okay, 2 is now being given to. So this is more or less the game that memory management plays. I hope it's logical. So fragmentation, if you look at this, if I were to play this game over time, where people take one room, over time you realize that things will be spread out. Now, processes can work faster if often their memory is consecutive. If it's consecutive, that means that even if I'm doing a loop, I can go with sequence in the memory. Just but if it's no more in sequence, that means I'll hit this, I'll jump to another location, and memory often is brought in blocks. When you take advanced, so those who are under advanced database, some of the algorithms that we do there, when they say, okay, maybe merge, sort, and so on, all the algorithms there are aware of the fact that memory is something that is limited. So things are going to go in, things are going to come out. And that means that even when you're sorting, you have to be aware of, okay, if I'm sorting and I'm currently here, I'm the CPU, why don't I sort all the people in this room first? As opposed to, and that means that the location of things, when you write software, sometimes you don't know exactly where things are. You just declare a variable. Student, new student. Lecturer, new lecturer. You just create your variables. You don't really wonder. You don't ask, where is this thing in memory? Where is this thing in hard disk? You just do your thing. You do your big loop. And that's why often if you do a very large loop, it will be very slow. And if you ask a database, like if you query a database, sometimes you can get the results back very quickly. And that's because the DBMSs are very much aware of what is in memory, what's in hard disk. So if you ask him to do something, he can plan about it. He can say, well, I have 2 questions. Even though this one is the second question, I have the data in memory. Let me work on that one. If you are writing a normal program, you don't know, right? You usually just will have a variable. If it's Java, your variable is there. Okay, well, I made my variable, I accessed it. But you rely on the Java virtual machine to do that negotiation or work for you, right? But what the DBMSs do is, because they are just dealing with data, they can plan. And remember, data often has a predictable trajectory. If it selects, he knows that I have to get these names. So he knows where the names are. He knows where the IDs are. He knows where. So that's how some of the systems can improve on this. So fragmentation means that the data has been scattered. The worst case, so the worst thing that can happen to someone, a database, is if all the data is in different locations. That means that even something like select star, it's going to take a long time. Because everyone is going to be what? Coming from a different location on the hard disk. So if the disk is spinning, that means that if it's all in one track, it's just like music. If you are burning a music CD, you realize that it burns one track at a time. I don't know if you have realized that. It takes one track, burns it. Takes the next track, burns it. That means that he knows that if he's on one like circumference, he's along the same list to finish a song before it goes to the next one. The evil thing is, if you broke the music into pieces, you burn 1 kilobyte, 1 kilobyte. That means that it will be skipping a lot, right? Or it will be pausing a lot, right? So that's the fragmentation issue. If data is in sequence, and you're accessing in sequence, it's very fast. But the moment I'm accessing it, and the way I'm accessing it doesn't correspond to the physical location, right? Then I'll be in trouble. Because then when I start a little bit, then you'll say, oh, I have to go and find the extra data to satisfy you. So that's the fragmentation issue. Right? And with the memory, with this strategy, you can see that fragmentation can happen. Right? So for data itself, fragmentation can happen. For processes, fragmentation can happen. You can have a process which is living in different locations in memory. Okay, so now back to citing stuff. So if you hear the word MMU, it's the memory management unit. And what the memory management unit does is, in real time, as the programs are executing, it will be calculating the relocation, that is, the offset to move them, and checking to see if you are going to be what? Making a valid access to memory. So you have to check. Is it falling into one of the memory bases and memory limits? Checking your memory and limit. Checking each one. Right. Now, so we are just going to add a few things, and then we'll pause there and go back to scheduling. Oh, sorry. So when you have addresses in software, I think, depending, people might have heard of compile time binding. This one? Okay. So whenever a process is being loaded, remember in chapter 2, we're talking about the process control block. In the process control block, it had a list of your registers. It knew the files you were using. So in the list of registers, one of the things that it knows, the beginning, said it knows your base, he knows your limit, and he also knows your relocation, how to move you. Right? So sometimes this one, right, is something that hardware can help with. All three. So it means that anytime you are a program that is running, you can say, address number 1, the same way we're doing this thing, where the Ashesi, you can say, oh, Ashesi room number 1, or maybe not room number 1. We'll map you to some virtual location and then map you to some physical location. So it's not really direct. You have a number you are using. But what the memory management unit need to be doing is remapping all of these. So during process switching, so we say one process switches to another process. During that switch, these registers have to also be what? Be changed. Your base. So if I'm going from Word to Excel, I'm moving them about in memory. It means that what? The base, register, relocation, mapping has to be what? Has to be moved. And a new one loaded before you run. So that as you are running, then the algorithm is happening automatically with hardware. The hardware will handle it. Okay, when you were coming, this is her base, this is her limit, this is her relocation. We'll just be computing. It determines your range, what addresses are allowed for you. Okay, so for those ones, what has to happen is, there are different types of instructions that are there. Some of them would say move data into registers, move data into this address. So there are some OSs that start, and what they'll do is, if I have loaded your base and limit, and I've not put in, let's say, a relocation, then you know, okay, fine, I'm not relocating things. But if I load all three, so if I make the hardware, and then I say, okay, I have a relocation. Remember that if the relocation was 0, you weren't going anywhere. We're staying in the same place. But if I give you some other number, then that means I'm going to be moving you whenever you ask me to do a computation. So even though some addresses may be staying in the same place, you can be specifying just offset 0, not to move it anywhere. I hope you understand. If your offset is 0, you're not going anywhere. If your relocation is 0. So it means that if you gave me this sort of architecture, and you told me that I have a program which I want to live in a specific location. For example, your bootloader. When you are starting your computer, the first thing that loads and brings in, so the firmware starts. The firmware, that's the Lenovo or whatever screenshot, and then says, I'm loading from hard disk, or OS is loading. That one is there. But before the OS loads, there is something like a bootloader. The Linux people, since you did the CentOS, realize that it gives you a list of maybe three lists when you are booting Linux to pick. That is the bootloader. The bootloader, when he's starting, he does not necessarily have to deal with this whole relocation business. He just knows that I'm starting at 0. So when I say 0, address 0, 1, address 1. So it's compiled and loaded into a specific location. Right? So for him, there's no movement. But once the OS starts and he's dealing with multiple people, then he has to make sure that he loads these base limits and offsets so that people can be moved in and out. So whenever a process is switching one for another, he has to switch those. I hope you understand. Okay.
So supposing the rate that you use to process is full, the rate of the process is full.
It's full. Uh-huh.
So would that process is its limit?
Okay, so there are various techniques. So some OSs, right? Some OSs will just give you, I mean, if you keep asking for more, they won't stop you. So long as he can use, wow, it's not good. If you are the one running, right, and you ask for more memory, what some OSs will do is they will simply pretend that they have inflamed memory. And if you say, I want address number 100, you just say, oh, okay, I'll go and swap out some of your, because you can't be using all that memory at the same time. So there's this idea that even if you ask for more memory than you have, it can virtually appear to you that what? You have almost infinite memory. Right? So if you take your currently addresses are 64-bit, your 64-bit addresses, sometimes they are more than the memory that is there, right? But then it doesn't mean that when you ask for something, you give it to you. He always give it to you, right? So in C you can say malloc. In Java you say new. If you make new, he'll keep giving you new. But sometimes, so depending on the platform, for example, Java Virtual Machine. If you're running the Java Virtual Machine, you can run a program and say, I think there's a parameter you pass to it. I have to remember, forgotten. But for Java, for example, you can say that this program should run with only 512. And that means that the OS will then keep in mind that this Java program has been limited to 512. And that means when it gets to the limit, he can't make any more new things. He will have to what? Either delete some, or when he asks, so when you do new, it will crash and say Stack Overflow or other similar error. Right? So that is there. If that doesn't exist, then what the OS will do is it would honor your request, but then since you are not using all at once, he will take some of your things out into hard disk and bring, and which is what starts to cause a slow. Because when things are slowing down, one of the problems could be things are moving in and out of memory. Right? So your program is running all right, but it's now very slow. But some come into memory, go to hard disk, some go move back. I hope you understand the concept. Right? So the OS can be hinted or can be told in the case of JVM that this process should be limited to this amount of memory. So when you hit your limit, he won't allow you to keep allocating. I hope you understand. Right? But some of them, some programs, so that means the OS really can be hinted as to how much memory to give to process. But that would be, if you take, we did shared memory. So when we're doing shared memory, there was something like SHM open, and then I specify a size of memory, right? So that means that it's possible to find system calls in C, C++, where you can directly what? Specify how much memory you want. Say, oh, I want this memory, I want this memory, I want this memory, I want this memory. Right? The SHM one will actually keep it there. But if you don't have direct access to C or C++, then it depends on the settings of what? The Java Virtual Machine. How much has the Java Virtual Machine been told to use? I'm trying to see if I can remember. There was something that I was just... Oh, I remembered. Okay, I think I know where it is. This is for database class, but I'll just show you very quickly. New for... Oh, where did it go to? Okay. Just a sec. I'm just going to find a program that when you run has limits on the address range. Right. Please be good, please be good. Come on. Why? Okay. Sorry, this is taking too long. It might be better if I just found it myself. It's not in this place. Win 32 and oh, this is serious. Okay, so I was looking for a database manager that we had. Okay, it's taking a while. Okay. So I'll just leave it and go somewhere and continue, right? But what I'm saying is for Java, for example, they can limit the memory, right? So if you are running, let's say, a web server, and you want to run different components, maybe you have 4 gig of memory, you can say, okay, Apache, you use 1 gig, my database, use 1 gig, maybe my file server, use 2 gig. So you can tell the OS to bound them, to limit them, or to say this is how much you keep in memory. The others, if you ask, either you go out, or if there's nothing to do, I'll kill you off. I hope you understand. Right. So it's in the system calls. If you find the system calls, you'll be able to do that. Right. Now, when it comes to memory, there are many times, different locations where memory addresses can be determined. The first one is a compile time. We don't have a compilers class. Right. Usually, a compilers class, they discuss how do you turn the human language, like the C I've written, into machine language. So what usually happens for a program is you take the instructions of the code. Do I have PHP? Okay, let me do something very simple. Okay, so what compilers will do is, anytime they are given something like this, so this is just brief, the whole compiler class. The moment the language, you give it some code to run, the first thing it needs to do is to go through and figure out what are all the variables that are in use. Right, so once it goes, it will say, okay, I see that you are using 3 variables. There's I, J, X. So these are some of them explicitly defined, right? There are some variables that are implicit, right? Where someone does some calculation, it doesn't store it. But all those, it needs to keep track of. In this case, I'm not doing something like that, right? You keep track of the variables. And then that means that he has to then plan and say, for every variable, where am I going to store these variables? Right? So if he knows that he has, let's say, some contiguous memory, we can say, okay, what is the size of an int? You tell them what an int is, what, maybe 64 or 32. I think I'm using 32. So we say, okay, address 0 to 31 is where my x is going to be. 31 to, okay, we are doing, I said 32-bit, right? Okay. 63 is where my second one is going to be. 64. X, Y, sorry. I didn't put them in order, right? In the compiler class, depending on how you went through the code, some people scan from the bottom, some people scan from the top. But scanning from the top is the reason why some of the languages, they will say when you're declaring variables, it has to be at the beginning. I don't know if you have realized that. Like even your C declaration, they'll say it has to be at the top. So when he starts off, he knows that these are all the methods I'm dealing with. These are all the variables. So he plans ahead and says, so I'm going to make space for them at the beginning. He plans for them, right? And then the second part is he will go through the code to say, okay, if I'm doing some if-else, usually that means I do some comparison, store some value, and then I jump. So for these ones, some of these may have some extra variables. So it has to go through. So there are some variables you declare, some are implicit. Now, if this code is going to live in a fixed location, right? So there are some addresses which they'll say they are absolute addresses. Absolute meaning that the address has been computed to be fixed. That means that it would say, have people done COA at all? Okay. So there will be something like, no, people haven't done that. Okay. Okay, so when you are usually moving in data into memory, there are different types of instructions in assembly. One of them can be load, so I just write English, from some address some specific value. Right? That means that it's compiled. So that's the one of the questions you're asking. Is something, can it be that someone is told to move something from a fixed address? Yes. Your instruction can say, go and load, and in your assembly, it can be there, compiled already, hard-coded. Go and move this from address 0099. Move it in. That means that if at that time you try and access, and it's not your base and limit, you will what? You will crash. The OS will catch you and say you are trying to access memory outside of your location. Another approach is, it can say load from some register. Load an address using address in some register. This is another way to load. That means that I can calculate the address location. So that maybe register 1, I'll put in 0999 before I load. So one is I can hard code a number. Another is I can make it based on a register value. Right. So depending on the programming language platform, so you write your high-level language, C or Java, and the JVM will then handle all this movement. It will then say, okay, let me make a variable for it. Go and calculate the offset. Because there are some programs which don't live in a fixed location. Some programs, the first time he's running address number 100. Next time he's running address 2000. And this happens in real life for some of the programs. The ones that don't move are usually the bootloader. Some of the OS code, it doesn't move. He stays in the same location. He's compiled, he's told, you stay. And I think if you read about bootloaders, some of them, they'll tell you to put it at the beginning of the hard disk or some specific location. He expects to run from some location. He comes in, he's running. But there are some programs which will be what? Will be moving around. So those guys cannot have absolute addresses. They must have dynamic addresses, meaning that when he's loaded, he will have to what? Either during load. So the lists I've given there two. Right. At compile time, if you know exactly where the program is going to run, right, you can calculate all the addresses and list it in the assembly code that this is address number 900, address number 1000. But sometimes you don't even know where it's going to run. In that case, at load time, that is when the program is being prepared to be brought into memory. Then the loader, so there's a, right. So there is a program that will load, that handles the loading, and there's also someone who can link. So linking means that there are different pieces of a program. Right now, when you are, I think when we're doing the threads, I was saying that sometimes we are compiling, you say something like that's pthread or something. So that means that even though the compiler himself sometimes has to be told, oh, these are in different pieces. Your libraries are not in one place. It's not you that wrote it. So it has to link from your code so that your system call can what? Can work. So there's a linker to who will go through your code and say, oh, this system call, he's trying to jump. Remember that like a function call is like a jump. You jump from one, it's like a go-to. Though they say we don't use go-tos anymore. Just a jump from one location to another. So what a linker and loader will do is, say, okay, when I'm loading, go and ask the linker guy the address of all the functions so that I can jump to them properly. So your same code, you can copy it and bring to my machine. But what the linker will do is when it's pulling the things, he will give me different addresses because maybe my libraries are in a different location, yours are in a different location. So we are all making function calls, send input, fopen, but the addresses are what? They are all different. So there are some programs which load with other things. So when they are loading, at that time is when all the calculations for where all the addresses and function calls, that's when you do them. So that's why the second one is at load time. At load time, some of the addresses may be determined. Right. The last category of addresses is the ones that are usually for the interpreted languages like PHP, Python, and so on. That means at execution time, that is when you try and determine what is my X, what is my Y, where is it going to be. So as it's executing, the program has to know or keep track of all the variables. That's why all the interpreters, they don't necessarily run straight machine language. So Java runs straight Java virtual machine. So when it makes and says, oh, I want a variable, the JVM will check and say, okay, this variable, let's put it here. If it's PHP, as it's running, the interpreter will say, oh, he made an int, where should I put it? He made a file, where should I put it? He made a database connection, where should I put it? It's not hard-coded. It's not compiled. That's why some people think that the languages that are compiled may be faster than the interpreted ones. Because there's no extra need to go and check, oh, where is this function going to go? Where is this address call going to go? Right. So the absolute, if you can compile and get everything absolutely, great, fast speed. But if it's absolute, it means that what? You can't move the program around the memory. If it comes, you can't move them around. Right? Now, some programs, some of the addresses, they don't know until load time. Here, at this point, at compile time, you can determine absolute addresses, right? If you know the absolute ones, you can determine at compile time. And so this program is going to be running in memory location 0 to 1000. It's always going to be there. You can then compile and put the addresses in, right? If you don't know, and sometimes it doesn't know, so the code you've been running, the C programs, you have been using some libraries. The libraries are not in your code. But at the same time, you should be able to copy your code, give it to me, and it should run. So that means that when the program is being loaded, some parts are going to be modified. The function calls. He'll say, oh, this function, fopen, in your program or in your computer, it's a certain location. In my computer, it's a different location. In someone else's computer, it's a different location. So that means that at load time, some of the addresses are what? Determined. Usually the function calls, system calls, those are going to be linked in. But then there are also some variables which are not even known at all. When you say new students, especially those doing classes, you make instances of things. That means that even at compile time, he doesn't know. He just knows that he should ask for something new. The address does not exist. But when he's running, when he says new student, then he'll go and get that address based on the platform. If it's Java, Java will give him an address that, oh, I've made a student for you. If it's C, the system will go ask the OS to get in some space. So at execution time, you can also determine some of these addresses. Right? So it's a mixture of these three. Right. For the libraries as well, some of the libraries, so if we say, you may need this if you are installing a lot of like software on CentOS or something. Windows, you may not encounter this in Windows. Windows tends to have nice setup. You click next, you are done. The Linux people may run into this more often, where for some compilers, when you compile, it means when they say statically linked, it means that it didn't wait till runtime to actually determine the address of the function. What it did was, when you were compiling it, it used the addresses that were there in the libraries on the system to determine all the addresses. And for those ones, when they are statically linked, it means that it may be hard to move the code from one location to another. Right? A lot of the Linux software, when you install, I don't know, these days people just do yum install and apt get, and then some magic happens. Right? And it handles all the compilation. But what happens is, some of these installers in Linux, what they'll do is, they'll download the source code, they'll do some compilation, and then, so some people say, oh, Linux machines can be fast. And I think some of the reason is just that they are compiling some of the things. That based on your computer, if you have certain libraries, and you download some code, you compile it. If he statically links it very fast. Dynamically linked means that the function, he knows he has to call it, but he doesn't know the address. The code is portable. But at the time when he's being called, if you say fopen, you wait. And then you ask the OS, please, in your list of libraries, is there a function called fopen? So you realize that if you made a function that doesn't exist in C and you're trying to run it, you say this function doesn't exist. Right? If it existed, some of them will try and find the location, pull in the library, and make the system call. Right? So that's the difference between statically linked and dynamically linked. So statically linked, it means the libraries are there, the functions are there, and it's put the exact locations that are on your machine. It's put it there that, oh, fopen is here, put is here, get is here. It's put it in. But dynamically linked means that anytime you make a system call, at least the first time, you would ask and query to find out where exactly is this function, where is it leading to. So it's like a little stub. So in the book they say stub, but it's just a little piece of code that will do the resolution before it carries out the system call. Right? So those are the ways that libraries are linked in. Right. So as far as memory, so I'll be stopping here. I think there are so many things we talked about today. As far as memory, there are a few strategies for placing things. Right. All of these have advantages and disadvantages, but we'll just talk about them naturally. Right. So one of the things that you can do when someone asks for a room, so there's best fit, first fit, worst fit. So let's do this. So assuming that EMS people left. So EMS people, so EMS are these people. 3, 4, oh, sorry. Oh, I've seen what I've done. That's so interesting, eh? 3, 4, 5, 6. It's not static, right? It's dynamic, what I've done. So when I delete one number, all the other numbers go. Okay, and assuming that Ashesi also leaves some spaces. So let's say HRC vacates their last two spaces. They also leave. Right. So that means 19 and 20 are available. Let me also, okay, let me leave, take 18 away as well from HRC so I can free up. Let me also take away from HRC 11 and 13. 12 and 13. Right. So right now what I have here is a hotel where there are many spaces. Right. Some spaces are there. So 3 to 6 is free, 12, 13 free, 18, 19, 20. These are free. Right. So the first strategy, so this is the easiest one, first fit. Right. So first fit means that whenever someone asks for something, the first space you find. So there are some locations where you attend an event. First fit means that what the person will do is, the first seat he sees, he'll put you there. Say, oh, well, hello, Mr. Marv. Welcome to the event. First, oh, yeah, there's a seat for you. Sit down. Just stamps you. That's first fit. The first space, and that's what? Very fast. He doesn't have to worry a lot. Very quick. Right. The next one is best fit. Right. So best fit, what you try and do is try and put someone in a location which is as close as possible to what meeting his requirements. So if you are the first, if you are coming to the hotel as a one person who wants a room, you don't put me in room number 3. That's not close enough in size. You then go and find the place, so maybe number 12 or number 13. That is the closest in size to what I want. So if I wanted 1 or 2 rooms, in first fit, you put me in what, 3 or 4. That's wherever you find me. If I want 1 room, you put me in 3. If I want 2, you put me in 3, 4. Right. For first, that's what I'll do. For best fit, if I want 1 room, 12, 13 is closest to what I have. I want 1. You found a space that has what, 2. So you can put me in one of those. That means best fit. As much as possible. Okay, so think of it this way. If you were seating people in an auditorium, a single man shows up. If you put this person, and restaurateurs and those who do booking do this, you go and put a single person on like a big table alone, like a 12-seater table. Because maybe somebody will come and would have about 12 people. So the idea of best fit is, I'll put you on a seat that is as much closer to the requirements of what you are going to use. So if you are a one person, if I can find just a place where there's 1 room space between the whole block, I'll go and put you there. If there's 2, so I'll use that strategy. If you are 2, I'll try and put you in the 2. If not, I'll go to a place where maybe there are 3 spaces or to 4. I won't go and say 2. Go and put the person in a large block of space. So let's say 2 people. 2 people have come to this hotel. For best fit, you put them in 3, 4. That's best fit. That means the first rooms you see, you put them there. For best fit, you try and put them in a location where the space matches what they want. So it's like you're trying to fill in as much as you can without leaving big spaces, or like preserving your big spaces. Right? And you can see this when you're ordering or trying to book a room or maybe trying to book a table. What they'll do is, they won't say, oh, one person you came to book, let me go and put you on the 5-seat table. No, they'll try and put you on a 2-seat or 1 seat. So that's the best fit. So for hotels, they'll say, okay, we'll put you on that because maybe someone else will come. Because if I put you in a large space, what if someone comes for a large space and all of a sudden what? I've taken one from it. I can't book the person there. I can't make the person consecutive. So they all have their advantages. So the first fit is very fast because what? You don't worry yourself too much. Just say, oh, first space I find, there you go. Best fit, you can say, oh yeah, let me try and find the place that is closest to what you have. So if I have 2 spaces at 12, 13 and you are 1 person, I'll go and put you there. If there are 2 people, I'll fill in them. Yes, I fill that space. Right. And the idea being that if you are able to put it into the place that's as best fit, you can fill in the holes. But then the problem is, if you are doing that, so first fit is nice, but first fit, it may not always work because if you could plan, I mean, if you think of yourself like an real estate agent, if you can plan and you know where all the resources, people say, I want to put up a church, I want to put up a football field, if you knew ahead of time, you can plan things. You can say, okay, this place is where the residential is, this place is where the commercial, you can plan things out. Right? So it doesn't mean that, it means that first fit may not always work. Right? You can't just blindly put there because there are going to be issues. Maybe things are going to be fragmented, people are not in the location they prefer. Right? Best fit may also not work. Because if one guy comes and says, oh, I want a room, and you say, okay, this is the best fit I could find for you, you could do this. But this best fit, there will now be all these little spaces, one, littered around. So that some big people, when they come, they don't have any space. Right? Because all these people you have, oh, you are fitted in. Maybe if I had put all the little people in some bigger space, and then someone comes and I could find a few blocks that were together, some 2, 2, 2. I could, but now that I put one here, now I have this 1, 1, 1 spread out. I can keep doing this game if I have twos all out. Okay. So that is the problem with best fit. It's nice because you can try and sometimes be lucky, use up as much space, leaving the big blocks. But the problem is if you do it too much, you can have all this fragmentation. Because a lot of programs will not necessarily fit exactly. They'll come, they want to use, there's some left over. Right? And the last one, so this sounds counterintuitive, but the last one is worst fit. Right? Which is, well, when someone comes, go and give him the biggest space he can find. Right? So that is a little bit like going against the best fit idea, because in the best fit, when he puts you there, the space that's left over is what? Very small. So with the worst fit idea, you'd say, okay, let me find a huge tract. That way, at least if I place somebody, there's extra space left over. It won't be one. Because if it's one and someone says, well, I want consecutive, then you can't. I just say, well, let me go and put you in the biggest space I can find. Right. So these are 3 algorithms. Question? In the first location you can find. Right. So the worst fit. So the difference between first fit, he doesn't try to optimize where you are being placed. He just says, the first space I see, I'll put you there. It's just like sitting in a party. Just pick someone, first space I see, you sit there. With best fit, your strategy is now, let me go and find for you a place that will match the size of who you are. So if you are one person, I'll try and find a single seat space for you. The next is I'll go and try and find 2 seat, 3 seat, and so on. But the worst fit is the inverse of that. To say, don't pick the first, don't pick the last. Take your time. Figure out the place that has the biggest amount of space and put the person there. Right. And that means that, so remember the problem with best fit was sometimes when you are placing someone and they are a little bit left over, you can end up fragmenting the area because they are made space of 2, 2, 2, 2 around. And you say, oh, well, let me put one person here, then you put one, remainder one. Go and put another one, remainder one. You do all this remainder one. After a while, you have these little fragments, spaces littered all over the place. But if you are going to say worst fit, well, let me find the biggest space, put people in. Then it's likely that as you put, you may have bigger spaces available. That means that whenever you place something, you want the remainder left over to be usable. Right? Because for best fit, someone is saying, okay, I want 999 megabytes. There's 1,000 megabytes. You put in there. There's 1 megabyte left over. You keep doing that game. There'll be all these little memories left over. Because some programs are not using exactly the free space blocks available. Some are using a little bit less. Because you have to find a place where you fit. So as much as possible, you put him there. But then what? You're left with this little leftover spaces that are left. But with worst fit, that means that you pick the biggest area you can find and you go and fit him in. And in the biggest area, hopefully, the space left over, that's the point, the space left over is also usable. It's much bigger than if you're doing best fit. Meaning that even if it's just 1/2 an inch left, you put the program there, there are these few megabytes left. You put it there are these few megabytes. And if you added up all the megabytes, there's a lot. But because you are doing best fit, there are all these spaces. It's like car parking. You can use the same analogy for car parking. First fit is what? The moment you come, first space you found, you park. Right. And then what? Best fit. You go and find space. Actually, the car parking one works if you think about it. Because you would say, okay, let me try and find the space where I'll fit into the closest. But people are fitting. But anytime he fits, he's left some over. But what if he said worst fit? Worst fit means that what? He'll come next to, there's a big area. He won't try and go and find a small area. He'll come to the big area, park. The next guy will come, this is still the worst area, right? You come. He'll be consecutive. He'll fill it up for a while. At least the leftovers will be what? Usable. You can play this game as well with your friends in the car park, moving them around. And then you always done. best fit, worst fit. Right. So those are, hello. So they all have advantages. Please, in this class, there are many strategies. There isn't one. So they all will have advantages, disadvantages. Often, it will have to be, you run. So what we usually do, even for most code, what we'll do is we'll run it for a while and see the behavior. Because there are some test benches that if you use it, someone comes up with best fit. So all these have come up. Or someone could try and do something that's a little bit hybrid. Depending on the size. I would probably do something hybrid. Depending on the size, you could decide, okay, for this best fit, for this worst fit. Or you could do something statistical. That is, watch and see. What is the probability that if I assign people 1 to 2 in the future, I don't have any trouble? What is the probability that I put people 2 to 3, 2 to 4? So you can do something more like AI statistical to solve it. But they are just showing you the different strategies in plain sense. First fit. But first fit is very fast. I mean, that's the nice thing. Best fit, of course, you can use as much space as you want, making sure that you are optimizing. But in this case, you are over-optimizing potentially because there will be what? Some little leftovers. Right. So in coding sense, what happens is, for a lot of systems, they will do defragmentation. And my hair, this is serious. My word is not working. I was doing this for consecutive, but now my word won't even come out of my head. Consecutive is not working. Okay. No, that's not it. This is what happens with too much coding. It will happen to you. Like the OS right now describing it, it has used up all the memory, all the English and all the tree is gone. So after class, usually I'll have to sit down and then deload all the information from my memory so I can be a thinking person. I even said people. The English is now leaving my head. Okay. So back to the fragmentation, right? So what it means is a strategy for a lot of systems is when they run for a while, because there are all these spaces, now and then they'll consolidate. That's move things around to make space. That means that if you are doing best fit, you don't just keep sticking to best fit. After some time, you can pause the system and then move people around a little bit so you can rearrange. So sometimes this can be done. Because if you rearrange, but even the rearranging, you have to have a strategy. Some people can say, oh, maybe when there's nobody running, then you start rearranging. Or someone can say, oh, do it bit by bit. Anytime you get some free time, you can rearrange some of them to make space, right? So you can employ some defragmentation to handle it. Okay, so the hotel room one was the one I was describing, right? So for today, what we've discussed, there are many things. It's the memory chapter. The different types of addresses, logical and physical. Right. We knew that the physical is the physical one, but the logical is like you get a ticket that you can use to find your physical address. But that also means that the system has to keep track of who is actually in a physical location and who has not yet been booked. So that if you have not really been put in a physical location, when you come, you may be reassigned somewhere else. So the three was have a hit, a miss or a store. Hit meaning you found it, miss meaning you couldn't find your space. Even though you had a ticket, there wasn't a space, they had to make one for you. Store means that if you try to access something and they don't have a space, have to bring the data for you. You have to wait while the data is being moved. Right, so that's the store. The special registers was base, limits, and relocation. Right. And for memory protection, what it has to do is make sure that you always access data within the range that has been assigned to you. In the text, they tend to use only one. But my point to you throughout the example with the hotel is, for programs, they may have several base limit registers. Right. The newer OSs now, processes don't all live in one beautiful consecutive space. You may think that your program is running, it says address 1, address 2, address 3. But address 1, 2, 3 could be remapped. 1 could be at 10, 2 could be at 20, 3 could be. So even though it gives you the sense, this virtual 0, 1, 2, 3, it is remapping these so that it's accomplishing this base limit thing. So one person will have several base limits to sort of capture the fact that he has several blocks of memory. He doesn't have one consecutive space. Right. So the hardware that's used to do this, checking just the physical is just about checking the base and the limit. But if you are doing logical, which is what most computers now are doing, they will have to do that calculation, figure out the address you've been given, virtual address. What is it being assigned to? Find the physical and then check. Even the physical, where are you going to? And then once it finds it, then you can say, are you allowed to or you're not allowed based on your requirements. Right. And we talked about binding. So binding is trying to compute the address of some variable or some function. So we say at compile time, the compiler can go through. So when you hit compile in Java or C, it goes through, tries to determine the addresses of these variables and function calls. Right. At compile time it can, but they are not all things that it can determine. Especially when things are going to be used outside of the system or it's going to be moving. If there's a library it's using, he may not know. If you do static linking, that means that he can, during compilation, figure out that this function is in this library at this location. You can figure that out. That's the location. But sometimes it can be dynamically linked, which we tend to prefer. There's a little bit of a slow, like the first time the function is being called. But that just means in the function call, before he's called, he has to determine exactly where the function is located. So the code is relocatable. The code, you can move from one machine to another. So that when he's running, when he calls a function, you go and ask, okay, library set, where do I load this from? And you tell him the address. Right. So there's load time. So when your program is being brought into memory, it can figure out the addresses that are left. Right. So it means that the programs which are relocatable, there are some programs that they don't have to be put into a fixed location because the address computations there are made dynamic. In that before he writes to a variable, you try and calculate the address. So that means he knows, okay, here's my base, let me add something. Or here's where the code I am is. Here's some offset. Right? So you can use that approach for load time. Execution time, still, there are some things you don't know about, especially if you are doing new, as making new classes, new objects, and so on. You will not know until what? You start running the code. So in that case, at execution time, some things may also be determined. The dynamic loaded library, that means execution time, that's when they are coming in. Your new making objects at execution time, that's when it's knowing the addresses of the things. Right. And finally, we talked about the three algorithms. There are more, but three strategies: best fit, first fit, worst fit. But there are some, when we talk about replacement, so this is when things are coming in. This is a strategy. But next class, we'll look at replacement strategy, meaning that once the data is there, what if I want to kick someone out? That one too, there are a few algorithms we can use. So someone can say, I think you know some of this already. You can say, okay, let me remove the least recently used, the most recently used. There are all these strategies, but they all have advantages like this and disadvantages. So for today, it's best fit, first fit, worst fit. And that is the end for today. Right. So thank you very much. Now I'm going to, before you leave, so what I'll do is, there is, sorry. Okay, so I am preparing, so what this will do is, I'm going to add, there's a section in the syllabus for some research that you can do, so I can grade and add to your grade. So it's not anything difficult. What it will do is, so I'm doing the outline, so it's going to ask you to pick an operating system. I've listed some, so Windows Mobile, iOS, we'll make the slot, so we'll put you in, right? And there's an outline saying that for each of the items, go and find 2 or 3 references, and write a short summary about it. So that means if it's Android, you pick the first one. So system architecture. What does Android use? You find good references. You list, Android supposedly maybe they use hybrid or they use monolithic. You can find. Right. Then it says multiprocessing tasking. How does it work? You find references. User interface. You find references. Files, memory, power, security. Rise and fall is like the history. How well is it doing? Is it doing well? Then you try and justify, okay, it's doing well because of. So this is an outline that we'll put up this week so that people can start writing on this. Just 1 page for each section. Right. So this will go up this week. 1 page for each section. For each. 1 page max. So in 8 pages. But 1 page max. So if you find, please calm down. If you find a reference and in 1 paragraph you can explain the code. But don't write more than 1 page for each item. So that's the limit. 1 paragraph for each, but limit 1 page. But find reference for each item still. For this one I found a reference. Rewrite the phrase, then you move to the next section. So one paragraph, the minimum, one page at most for each item. There are 8 items now. Yes, mademoiselle.
Yes,
Hey, it's okay. Yeah. Yes, I don't know. You can invite her. These are the last days. She has to manage herself. This one. The piece is for grade. Everyone should. So if you haven't, go and put yours there.
I'm moving right now.
Please go and put yours there.
I just thought it was for this practice.
So everyone has, I think about 50 people have put up now. So what I'll do is I'll download and then arrange so that everyone can read. And then I'll do a quiz. I'll pick some.
Will you give up marks?
You'll get marks for putting up. We won't do it this week. This week we are going to do scheduling quiz.
You have that track, can you?
The scheduling so not Wednesday
there.
because my videos don't have audio.
Yeah.
My videos don't have audio, so I have to re-record my videos.
So you have to teach scheduling again in the class?
No, I'll record myself. I'll just take snapshots, go through. Hey, where did my thing go?